Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. The phenomenon commonly referred to as rust is, in its most fundamental chemical description, a hydrated iron oxide, predominantly composed of iron 3 oxide in its hydrated form, which is expressed by the chemical formula Fe2O3 with a variable number of water molecules associated with its crystalline or amorphous structure. This substance, which appears as that familiar reddish-brown flaky coating on the surface of iron and iron-containing alloys, is the visible manifestation of a complex series of electrochemical reactions that have been occurring on the surfaces of iron objects for as long as human beings have been smelting iron from its ores, which is to say, for approximately 3,200 years, dating back to the widespread adoption of iron smelting in the early Iron Age, around 1200 BCE in the Eastern Mediterranean region. The process by which metallic iron is converted into rust is properly termed corrosion, and it is, at its most essential level, an electrochemical process, meaning that it involves both chemical reactions and the transfer of electrons between different species. The corrosion of iron requires, at a minimum, 3 components to proceed: the iron metal itself, which serves as the material being oxidized; water, which serves as the electrolyte that permits the flow of ions between reaction sites; and dissolved oxygen, which serves as the oxidizing agent that accepts the electrons released by the iron. In the absence of any one of these 3 components, the rusting of iron will not proceed at any appreciable rate, a fact that has been well established through countless laboratory experiments conducted over the past 2 centuries. The electrochemical nature of iron corrosion can be understood by considering that, on the surface of a piece of iron exposed to a thin film of water, there exist simultaneously 2 distinct types of electrochemical reactions occurring at different locations. These are classified as anodic reactions and cathodic reactions, and they are spatially separated on the metal surface, though they are electrically connected through the metal itself and ionically connected through the electrolyte solution that covers the surface. The anodic reaction, which occurs at sites that are designated as anodes, involves the oxidation of metallic iron. In this reaction, an atom of iron in the metallic state loses 2 electrons and enters the solution as a ferrous ion, which is to say, an iron 2+ ion. This reaction can be written as Fe yielding Fe2+ and 2 electrons. The standard electrode potential for this half reaction is negative 0.44 volts, when measured against the standard hydrogen electrode, which indicates that iron has a strong thermodynamic tendency to undergo this oxidation reaction. At the cathodic sites, which are spatially separated from the anodic sites on the same metal surface, the electrons that were released by the oxidation of iron at the anode are consumed by a reduction reaction. In neutral or slightly acidic aerated solutions, the predominant cathodic reaction involves the reduction of dissolved oxygen. In this reaction, 1 molecule of oxygen, which consists of 2 oxygen atoms, combines with 2 molecules of water and 4 electrons to produce 4 hydroxide ions. This reaction can be written as O2 plus 2H2O plus 4 electrons yielding 4 OH minus ions. The standard electrode potential for this half reaction is positive 0.40 volts versus the standard hydrogen electrode. The overall cell potential for the corrosion of iron in aerated neutral water is therefore approximately 0.84 volts, which represents a significant thermodynamic driving force for the reaction to proceed spontaneously. The ferrous ions produced at the anodic sites and the hydroxide ions produced at the cathodic sites migrate through the electrolyte solution and eventually encounter one another, at which point they react to form ferrous hydroxide, FeOH2, which is a greenish-white precipitate that is only sparingly soluble in water, with a solubility product constant of approximately 4.87 times 10 to the power of negative 17 at 25 degrees Celsius. This ferrous hydroxide is not, however, the final product of the corrosion process. In the presence of additional dissolved oxygen, the ferrous hydroxide is further oxidized to ferric hydroxide, FeOH3, which has an even lower solubility product constant of approximately 2.79 times 10 to the power of negative 39 at 25 degrees Celsius. This ferric hydroxide is an orange-brown precipitate, and it is this substance that, upon partial dehydration, forms the familiar reddish-brown rust that is observed on corroded iron surfaces. The thermodynamic driving force for the corrosion of iron can be understood in terms of the fundamental tendency of metallic iron to return to its thermodynamically more stable oxide state. It is a fact of considerable significance that nearly all of the iron found in nature exists not in the metallic state, but rather in the form of various iron oxides and iron-containing minerals. The most abundant iron ore is hematite, which is composed of iron 3 oxide, Fe2O3, and which contains approximately 70% iron by mass. Other important iron ores include magnetite, Fe3O4, which contains approximately 72.4% iron by mass, and siderite, FeCO3, which contains approximately 48.2% iron by mass. The extraction of metallic iron from these ores requires the input of considerable energy, typically in the form of heat provided by the combustion of coke in a blast furnace operating at temperatures between 1500 and 2300 degrees Celsius. The metallic iron thus produced is in a thermodynamically unstable state, and the process of rusting can be viewed as the gradual return of this iron to its thermodynamically preferred oxide state, a process that releases the energy that was originally invested in its extraction from the ore. The Gibbs free energy change for the formation of iron 3 oxide from metallic iron and oxygen gas at standard conditions, which is to say at a temperature of 25 degrees Celsius and a pressure of 1 atmosphere, is approximately negative 742.2 kilojoules per mole of Fe2O3 formed. This large negative value indicates that the formation of rust from iron and oxygen is a thermodynamically highly favorable process, and indeed, in a purely thermodynamic sense, Every piece of iron or steel that exists on the surface of the Earth is in a metastable state, slowly but inexorably tending toward conversion back into iron oxide. The rate at which this conversion occurs is determined not by thermodynamics, but by kinetics, which is to say, by the rates of the various electrochemical and chemical steps involved in the corrosion process. It is worth noting at this point that the term rust, while commonly used in everyday language to refer to any reddish-brown corrosion product formed on iron, actually encompasses a variety of different iron oxide and iron oxyhydroxide phases, each with its own distinct crystal structure, color, and properties. The most commonly encountered phases in rust include hematite, magnetite, goethite, and lepidocrocite, and the relative proportions of these phases in any given sample of rust depend on the specific conditions under which the corrosion occurred. Hematite, whose chemical formula is alpha Fe2O3, is the most thermodynamically stable of the iron oxides at ambient conditions. It crystallizes in the rhombohedral crystal system, belonging to the space group R3c, with lattice parameters equal to 5.036 angstroms and C equal to 13.749 angstroms. Hematite is characterized by its dark red to steel gray color, and it has a Mohs hardness of 5.5 to 6.5. The name hematite derives from the Greek word haima, meaning blood, on account of the red color of its powdered form, which has been used as a pigment since prehistoric times. In the context of rust formation, hematite is typically found as a component of mature rust layers that have been exposed to elevated temperatures or that have undergone prolonged aging. Its density is approximately 5.26 grams per cubic centimeter, and it is antiferromagnetic below its Néel temperature of approximately 948 Kelvin, which is to say approximately 675 degrees Celsius. Magnetite, whose chemical formula is Fe3O4, is a mixed-Velos iron oxide containing both ferrous and ferric iron in the ratio of 1:2. It crystallizes in the inverse spinel structure, belonging to the cubic crystal system with space group FD3M and a lattice parameter of approximately 8.396 angstroms. Magnetite is the most strongly magnetic of all naturally occurring minerals, and it is this mineral that was known to the ancient Greeks as lodestone, the natural magnet that was used in the earliest magnetic compasses. In the context of rust, magnetite is typically found as a dark-colored, relatively adherent layer that forms under conditions of limited oxygen access, such as beneath the outer layers of rust on a heavily corroded iron object. Its density is approximately 5.175 grams per cubic centimeter. Goethite, whose chemical formula is alpha FeOH, is an iron oxyhydroxide mineral that is named after the German polymath Johann Wolfgang von Goethe, who was, in addition to his fame as a poet and dramatist, an avid mineral collector. Goethite crystallizes in the orthorhombic crystal system, belonging to the space group PBNM, with lattice parameters equal to 4.608 angstroms, be equal to 9.956 angstroms. and C equal to 3.0215 angstroms. It is characterized by its yellowish brown to dark brown color, and it is one of the most commonly encountered minerals in rust formed under atmospheric conditions. Goethite is thermodynamically stable at ambient temperatures and is the end product of the weathering of many iron-bearing minerals. Its density is approximately 4.28 grams per cubic centimeter, and it is antiferromagnetic below its Néel temperature of approximately 400 Kelvin, which is approximately 127 degrees Celsius. Lepidocrocite, whose chemical formula is gamma-FeOH, is another iron oxyhydroxide mineral that is commonly found as a component of rust. It crystallizes in the orthorhombic crystal system, belonging to the space group CM, with lattice parameters at equal to 3.07 angstroms, B equal to 12.52 angstroms, and C equal to 3.87 angstroms. Lepidocrocite is characterized by its orange to reddish-orange color, and it is typically the first crystalline corrosion product to form during the atmospheric corrosion of iron. It is metastable with respect to goethite, meaning that given sufficient time and appropriate conditions, lepidocrocite will eventually transform into the more stable goethite phase. This transformation proceeds through a dissolution and reprecipitation mechanism and is accelerated by the presence of moisture and elevated temperatures. The density of lepidocrocite is approximately 4.09 grams per cubic centimeter. In addition to these four principal phases, rust may also contain amorphous iron oxyhydroxide, which is a non-crystalline form of hydrated iron oxide that does not exhibit long-range crystallographic order. This amorphous phase is typically the very first corrosion product to form on a freshly exposed iron surface, and it gradually crystallizes into one or more of the crystalline phases described above over periods ranging from hours to years, depending on the environmental conditions. The presence of amorphous iron oxyhydroxide in rust can be detected by X-ray diffraction analysis, where it manifests as a broad, diffuse hump in the diffraction pattern rather than the sharp peaks that are characteristic of crystalline phases. The electrochemical mechanism of iron corrosion, as described above in its simplest form, is in reality considerably more complex than the basic anodic and cathodic reactions might suggest. The corrosion process involves numerous intermediate steps and intermediate species, and the exact pathway by which metallic iron is converted to rust depends on the specific conditions of pH, dissolved oxygen concentration, temperature, and the presence or absence of various dissolved species in the electrolyte. One important intermediate species is the green rust, which is a class of layered double hydroxide minerals containing both ferrous and ferric iron along with various interlayer anions such as chloride, sulfate, or carbonate. Green rust has been identified as an intermediate product in the corrosion of iron in various environments, and it is thought to play an important role in the transformation pathways that lead to the final rust products. The formation of rust on an iron surface does not proceed uniformly across the entire surface. Instead, The corrosion typically initiates at specific sites where the protective oxide film that naturally forms on iron in dry air, which is a very thin layer of iron oxide only a few nanometers thick, has been disrupted or is less protective. These initiation sites may be associated with grain boundaries in the metal, inclusions of nonmetallic phases such as manganese sulfide, surface scratches, or other mechanical damage, or regions where the composition of the electrolyte differs from the bulk solution. Once corrosion has initiated at these sites, the local chemistry of the solution changes in ways that tend to perpetuate and accelerate the corrosion process. At the anodic sites, the dissolution of iron produces ferrous ions that hydrolyze to form acidic solutions, lowering the local pH and further accelerating the anodic dissolution. At the cathodic sites, the production of hydroxide ions raises the local pH, which may have either beneficial or detrimental effects, depending on the specific conditions. The rust layer that forms on the surface of corroding iron is not, in general, a protective barrier that would slow or halt the corrosion process. Unlike the passive oxide films that form on metals such as aluminum, chromium, or titanium, which are dense, adherent, and effectively isolate the underlying metal from the corrosive environment, the rust layer that forms on ordinary iron and carbon steel is porous, poorly adherent, and riddled with cracks and channels through which the electrolyte can penetrate to reach the underlying metal surface. This is one of the fundamental reasons why iron and carbon steel are so susceptible to ongoing corrosion once the process has initiated. The rust layer does provide some modest degree of protection by increasing the diffusion path length for oxygen and other reactants, but this protection is far from sufficient to arrest the corrosion process entirely. The thickness of the rust layer on a corroding iron surface increases with time, but the rate of growth typically follows a parabolic law rather than a linear one, meaning that the rate of rust formation decreases as the rust layer becomes thicker. This is because the thicker the rust layer becomes, the longer the distance that dissolved oxygen must diffuse through the porous rust to reach the metal surface, where it is consumed by the cathodic reaction. The parabolic rate law can be expressed mathematically as the thickness of the rust layer being proportional to the square root of time, or equivalently, the square of the thickness being proportional to time. For mild steel exposed to a typical urban atmosphere, the corrosion rate during the first year of exposure is typically in the range of 10 to 50 micrometers per year, decreasing to perhaps 5 to 15 micrometers per year after several years of exposure, though these values can vary enormously depending on the specific atmospheric conditions. The process of rust formation is also influenced by the cyclic wetting and drying of the metal surface, which is a common occurrence for metals exposed to the atmosphere. During wet periods, when a film of moisture is present on the surface, the electrochemical corrosion reactions proceed as described above. During dry periods, when the moisture film evaporates, the corrosion reactions cease, but the partially formed corrosion products undergo further oxidation and dehydration in the presence of atmospheric oxygen. This cyclic process tends to produce a rust layer with a characteristic layered structure, with alternating layers of different iron oxide and oxyhydroxide phases, reflecting the alternating wet and dry conditions under which they were formed. Studies using cross-sectional microscopy and micro-Raman spectroscopy have revealed that atmospheric rust-on steel typically consists of an inner layer enriched in magnetite and an outer layer enriched in goethite and lepidocrocite, though the exact distribution of phases can vary significantly from one location to another even within a single rust sample. The study of iron corrosion and rust formation has a long history in the scientific literature, dating back at least to the experiments of Robert Boyle in the 17th century, who observed that iron gained weight when it rusted, an observation that was initially difficult to reconcile with the prevailing understanding of chemistry at that time. The electrochemical theory of corrosion was first proposed by Humphrey Davy in the early 19th century, and it was further developed by Michael Faraday, whose Quantitative Laws of Electrolysis, published in 1834, provided the mathematical framework for understanding the relationship between the amount of metal dissolved and the quantity of electrical charge transferred. The modern understanding of atmospheric corrosion of iron, including the identification of the various rust phases and the elucidation of the transformation pathways between them, has been developed primarily over the past century through the application of increasingly sophisticated analytical techniques including X-ray diffraction, Mossbauer spectroscopy, transmission electron microscopy, and synchrotron-based methods. It is perhaps worth reflecting at this juncture on the remarkable ubiquity of the rusting process. Iron is the fourth most abundant element in the Earth's crust, comprising approximately 5.63% by mass, and it is the most widely used of all metals, with global crude steel production reaching approximately 1.951 billion metric tons in the year 2023. According to data published by the World Steel Association. Every one of these nearly 2 billion metric tons of steel is thermodynamically unstable in the Earth's atmosphere and is subject, to a greater or lesser degree, to the inexorable process of corrosion. The rust that forms on a neglected garden tool, the rust that slowly consumes the body panels of an aging automobile, the rust that threatens the structural integrity of bridges and buildings, and the rust that gradually returns abandoned ships to the ocean floor are all manifestations of the same fundamental electrochemical process, the same thermodynamic imperative that drives metallic iron back toward its more stable oxide state, the state in which it existed for billions of years before. Human ingenuity found a way to extract it from its ores and put it to use in the construction of civilization. The color of rust, that characteristic reddish-brown hue that is so universally recognized, is determined by the specific mixture of iron oxide and oxyhydroxide phases present in the corrosion product. Pure hematite, when finely divided, produces a red pigment, while goethite produces a yellow to brown pigment and lepidocrocite produces an orange pigment. The overall color of a rust sample is therefore a function of the relative proportions of these phases, as well as the particle size and morphology of the individual grains. It is this same reddish-brown color that gives the planet Mars its distinctive appearance when viewed from Earth, earning it the name the Red Planet. The surface of Mars is covered with a layer of fine-grained iron oxide dust, primarily in the form of nanophase hematite and other iron oxide minerals, which were formed by the oxidation of iron-bearing minerals in the Martian regolith over billions of years of exposure to the oxidizing conditions of the Martian atmosphere and surface environment. The density of rust is considerably lower than that of the metallic iron from which it was formed. Metallic iron has a density of approximately 7.874 grams per cubic centimeter, while the various phases found in rust have densities ranging from approximately 3.4 to 5.3 grams per cubic centimeter. And the bulk density of a typical rust layer is even lower than these values due to the porosity of the rust structure. The consequence of this density difference is that the conversion of iron to rust is accompanied by a significant increase in volume, typically by a factor of 2 to 6 times depending on the specific rust phases formed. This volume expansion is responsible for the familiar phenomenon of rust jacking, in which the accumulation of rust in confined spaces, such as the joints between structural members or the interface between reinforcing steel and concrete, generates enormous expansive forces that can crack and spall concrete, deform steel plates, and generally cause extensive structural damage far in excess of what might be expected from the relatively modest amount of metal that has actually been consumed by the corrosion process. The electrical conductivity of rust is many orders of magnitude lower than that of metallic iron. While metallic iron has an electrical resistivity of approximately 9.71 times 10 to the power of -8 ohm meters at 20 degrees Celsius, the iron oxides and oxyhydroxides that comprise rust are semiconductors or insulators with resistivities ranging from approximately 1 to 10 to the power of 12 ohm meters, depending on the specific phase, its crystallinity, and its hydration state. This enormous difference in electrical conductivity has important implications for the electrochemical corrosion process, as it means that the rust layer that forms on a corroding iron surface cannot efficiently conduct the electron current between anodic and cathodic sites, which tends to localize the corrosion reactions and can lead to the development of deep pits and other forms of localized corrosion. The solubility of the various iron oxide and oxyhydroxide phases in water is also a matter of some practical importance, particularly in the context of water treatment and distribution. While all of the common rust phases are described as insoluble in water, they do in fact dissolve to a very slight extent, releasing ferric or ferrous ions into solution at concentrations that depend on the pH, temperature, and redox potential of the solution. At a pH of 7 and under aerobic conditions, the equilibrium concentration of dissolved iron in contact with ferric hydroxide is only approximately 10 to the power of -17 moles per liter, which is far below any analytically detectable concentration. However, under reducing conditions, such as those that may exist in the interior of a corroding pipe or in an anaerobic groundwater, the equilibrium concentration of dissolved ferrous iron can be many orders of magnitude higher, potentially reaching concentrations of several milligrams per liter, which is well above the threshold at which dissolved iron imparts an unpleasant metallic taste and a brownish discoloration to drinking water. The secondary drinking water standard for iron in the United States, as established by the Environmental Protection Agency, is 0.3 milligrams per liter. And the exceedance of this standard due to the corrosion of cast iron and steel water distribution pipes is a common water quality complaint in many municipalities. The magnetic properties of the various rust phases are also of considerable scientific interest. As mentioned earlier, magnetite is a ferromagnetic mineral with a saturation magnetization of approximately 92 to 100 ampere meters squared per kilogram at room temperature, making it the most magnetic of the common iron oxide minerals. Hematite is weakly ferromagnetic at temperatures between approximately 260 Kelvin, which is known as the Morin transition temperature, and its Néel temperature of 948 Kelvin, due to a slight canting of its antiferromagnetically ordered magnetic moments. Goethite and lepidocrosite are both antiferromagnetic, with Néel temperatures of approximately 477 Kelvin, respectively. The magnetic properties of rust have practical applications in the non-destructive testing of corroded structures, where magnetic methods can be used to estimate the extent of corrosion damage without the need to remove the rust or otherwise disturb the corroded surface. The rate at which iron corrodes and rust forms is governed by a multitude of environmental and material factors, each of which can either accelerate or retard the corrosion process to varying degrees, and the understanding of these factors is of paramount importance for the prediction of service life and the design of effective corrosion mitigation strategies. Perhaps the single most important environmental factor influencing the atmospheric corrosion of iron is the relative humidity of the surrounding air, which determines the amount of moisture that is available to form the thin electrolyte film on the metal surface that is essential for the electrochemical corrosion reactions to proceed. It has been established through extensive experimental investigation that there exists a critical relative humidity below which the atmospheric corrosion of iron proceeds at a negligibly low rate, and above which the corrosion rate increases dramatically. This critical relative humidity has been determined to be approximately 60% for clean iron surfaces in unpolluted atmospheres, though the exact value can vary somewhat depending on the specific conditions. Below this critical threshold, the amount of moisture adsorbed on the metal surface is insufficient to form a continuous electrolyte film capable of supporting the ionic transport required for the electrochemical corrosion reactions. Above this threshold, the adsorbed moisture film becomes thick enough, typically on the order of several monolayers to several micrometers, to function as an effective electrolyte, and the corrosion rate increases rapidly with further increases in relative humidity. The relationship between relative humidity and corrosion rate above the critical threshold is not linear, but rather approximately exponential, meaning that relatively small increases in relative humidity above 60% can produce disproportionately large increases in the corrosion rate. At a relative humidity of 70%, the corrosion rate of mild steel in a clean atmosphere is approximately 2 to 3 times greater than at 60%, and at a relative humidity of 90%, the corrosion rate may be 10 to 20 times greater than at 60%. These values are approximate and depend on numerous other factors, but they serve to illustrate the profound influence that atmospheric moisture has on the rusting process. It is for this reason that iron and steel objects stored in climate-controlled environments with relative humidities maintained below 50% exhibit virtually no corrosion over extended periods, while identical objects stored in damp basements or tropical environments may develop visible rust within days or weeks. The critical relative humidity for the onset of appreciable corrosion is lowered significantly by the presence of hygroscopic contaminants on the metal surface. Hygroscopic substances are those that have a strong tendency to absorb moisture from the surrounding atmosphere, and their presence on the surface of iron effectively increases the amount of adsorbed moisture at any given relative humidity. Common hygroscopic contaminants include sodium chloride, which deliquesces at a relative humidity of approximately 75.3% at 25 degrees Celsius, ammonium sulfate, which deliquesces at approximately 80% relative humidity, and various other salts and particulate matter that may be deposited on metal surfaces from industrial, marine, or urban atmospheres. When such contaminants are present, the critical relative humidity for corrosion can be reduced to values as low as 35 to 40%, meaning that corrosion can proceed at a significant rate even in relatively dry environments. Temperature is another important factor affecting the rate of iron corrosion, and its influence is somewhat more complex than might be initially supposed. In general, increasing temperature tends to increase the rate of chemical and electrochemical reactions, in accordance with the Arrhenius equation, which states that the rate constant of a reaction is proportional to the exponential of the negative activation energy divided by the product of the gas constant and the absolute temperature. For the corrosion of iron, the activation energy for the overall process has been estimated to be in the range of 30 to 60 kilojoules per mole, depending on the specific conditions and the rate-limiting step. This corresponds to an approximate doubling of the corrosion rate for every 10 to 15 degrees Celsius increase in temperature, all other factors being equal. However, the effect of temperature on atmospheric corrosion is complicated by the fact that temperature also influences the amount of moisture present on the metal surface. At higher temperatures, the rate of evaporation of the surface moisture film increases, which tends to decrease the time of wetness and thereby reduce the cumulative amount of corrosion that occurs over a given period. Conversely, at lower temperatures, the surface moisture film persists for longer periods, but the rate of the corrosion reactions is slower. The net effect of temperature on atmospheric corrosion is therefore the result of a competition between these two opposing influences, and the temperature at which the maximum corrosion rate occurs depends on the specific conditions of humidity and atmospheric composition. In many practical situations, the maximum atmospheric corrosion rate is observed at temperatures in the range of 20 to 40 degrees Celsius, where the combination of reaction kinetics and surface wetness is most favorable for corrosion. It is also worth noting that at temperatures below the freezing point of water, 0 degrees Celsius at standard pressure, the atmospheric corrosion of iron is greatly reduced because the surface moisture film freezes and loses its ability to function as a liquid electrolyte. This is the reason why iron and steel structures in very cold climates, such as those found in polar regions, may exhibit surprisingly low corrosion rates despite being exposed to harsh environmental conditions. However, the use of de-icing salts on roads and bridges in cold climates can create local environments where liquid brine solutions are in contact with steel surfaces even at temperatures well below 0 degrees Celsius, leading to severe corrosion in these localized areas. The presence of dissolved salts and other electrolytes in the moisture film on an iron surface has a profound effect on the corrosion rate, and this effect operates through several distinct mechanisms. First, the presence of dissolved ions increases the electrical conductivity of the electrolyte, which facilitates the flow of ionic current between the anodic and cathodic sites on the metal surface and thereby reduces the ohmic resistance of the corrosion cell. The conductivity of pure water at 25 degrees Celsius is only approximately 5.5 times 10 to the power of negative 6 Siemens per centimeter, which is quite low and represents a significant ohmic resistance to the corrosion current. The addition of even small amounts of dissolved salts can increase this conductivity by several orders of magnitude. For example, a 3.5 weight% solution of sodium chloride, which approximates the salinity of seawater, has a conductivity of approximately 53 millisiemens per centimeter, which is nearly 10,000 times greater than that of pure water. Second, certain anions, most notably the chloride ion, have a specific aggressive effect on the corrosion of iron that goes beyond their contribution to the electrolyte conductivity. Chloride ions are able to penetrate and destabilize the passive oxide film that forms on iron surfaces, leading to the initiation of localized corrosion in the form of pitting. The mechanism by which chloride ions break down the passive film has been the subject of extensive research and debate over the past several decades, and several competing theories have been proposed, including the penetration theory, which suggests that chloride ions migrate through the oxide film to the metal-oxide interface, the film-breaking theory, which proposes that chloride ions adsorb at flaws in the oxide film and promote its local dissolution, and the adsorption theory, which suggests that chloride ions adsorb on the oxide surface and catalyze the transfer of metal ions into solution. Regardless of the exact mechanism, the practical consequence is that iron and steel exposed to chloride-containing environments, such as marine atmospheres, road salt spray, or industrial brines corrode at rates that are typically 2 to 10 times greater than the same materials exposed to chloride-free environments with otherwise similar conditions. The influence of the pH of the electrolyte on the corrosion of iron is described by the Pourbaix diagram, which is a plot of electrochemical potential versus pH that delineates the regions of thermodynamic stability of the various possible phases of iron in aqueous solution. The Pourbaix diagram for the iron-water system, which was first constructed by Marcel Pourbaix in his doctoral thesis at the Université Libre de Bruxelles in 1945 and subsequently published in his influential Atlas of Electrochemical Equilibria in Aqueous Solutions in 1966, reveals that metallic iron is thermodynamically unstable over the entire range of pH values in the presence of dissolved oxygen, meaning that the corrosion of iron is thermodynamically favorable at all pH values. However, the rate of corrosion is strongly dependent on pH. In the pH range from approximately 4 to 10, the corrosion rate of iron in aerated aqueous solutions is relatively insensitive to pH because the cathodic reaction is the reduction of dissolved oxygen, which does not involve hydrogen ions directly. In this pH range, the corrosion rate is controlled primarily by the rate of oxygen transport to the metal surface. At pH values below approximately 4, the corrosion rate increases rapidly with decreasing pH because at these low pH values, the direct reduction of hydrogen ions to form hydrogen gas becomes an important cathodic reaction. And this reaction is not limited by oxygen transport. At pH values above approximately 10, the corrosion rate decreases significantly because the iron surface becomes covered with a more protective hydroxide film, and in strongly alkaline solutions, iron can achieve a state of passivity in which the corrosion rate is negligibly small. This is the principle underlying the corrosion protection of steel reinforcement in concrete, where the highly alkaline pore solution of the concrete, with a pH typically in the range of 12.5 to 13.5, maintains the steel in a passive state. Atmospheric pollutants play a significant role in accelerating the corrosion of iron and steel in industrial and urban environments. Among the most important gaseous pollutants in this regard are sulfur dioxide and the various oxides of nitrogen. Sulfur dioxide, which is produced primarily by the combustion of sulfur-containing fossil fuels in power plants, industrial boilers, and motor vehicles, is a particularly aggressive corrosion accelerator. When sulfur dioxide dissolves in the moisture film on a metal surface, it forms sulfurous acid, which subsequently oxidizes to sulfuric acid. The sulfuric acid acidifies the moisture film, increasing the corrosion rate through the mechanism of acid corrosion described above, and the sulfate ions that are produced have an additional deleterious effect by forming soluble iron sulfate, which does not form a protective barrier on the metal surface. Studies conducted in various locations around the world have demonstrated a strong correlation between the atmospheric concentration of sulfur dioxide and the corrosion rate of iron and steel, with corrosion rates in heavily polluted industrial atmospheres being as much as 10 to 100 times greater than in clean rural atmospheres. The oxides of nitrogen, principally nitrogen dioxide, have a similar though generally less severe effect on iron corrosion. Nitrogen dioxide dissolves in moisture to form nitric acid, which acidifies the electrolyte and accelerates corrosion. Additionally, nitrogen dioxide can act as an oxidizing agent, promoting the anodic dissolution of iron. The combined effect of sulfur dioxide and nitrogen dioxide on iron corrosion is generally greater than the sum of their individual effects, a phenomenon known as synergistic corrosion acceleration. In recent decades, the implementation of air quality regulations in many industrialized countries has led to significant reductions in the atmospheric concentrations of these pollutants, and a corresponding decrease in the rates of atmospheric corrosion has been documented. For example, in the United Kingdom, the annual corrosion loss of mild steel decreased from approximately 80 micrometers per year in heavily polluted areas in the 1960s to approximately 20 to 30 micrometers per year in the same areas by the early 2000s, largely as a result of the reduction in sulfur dioxide emissions achieved through the use of cleaner fuels and flue gas desulfurization technology. Beyond the general or uniform corrosion that has been discussed thus far, iron and steel are also susceptible to several forms of localized corrosion, each of which involves the concentration of corrosive attack at specific locations on the metal surface, while the remainder of the surface remains relatively unaffected. These forms of localized corrosion are often more dangerous than uniform corrosion from a structural integrity perspective because they can produce deep, through-wall penetrations in relatively short periods while removing only a small total amount of metal, making them difficult to detect by simple visual inspection or weight loss measurements. Galvanic corrosion, which is also known as bimetallic corrosion or dissimilar metal corrosion, occurs when two different metals or alloys are in electrical contact with one another in the presence of an electrolyte. In this situation, the metal with the more negative electrochemical potential, which is termed the anode, corrodes at an accelerated rate, while the metal with the more positive electrochemical potential, termed the cathode, is protected from corrosion. For iron and steel, galvanic corrosion is a concern whenever these materials are used in conjunction with more noble metals such as copper, brass, bronze, tin, or stainless steel. When carbon steel is coupled with copper in the presence of an electrolyte, for example, the corrosion rate of the steel in the vicinity of the junction can be increased by a factor of 2 to 5 or more, depending on the area ratio of the two metals and the conductivity of the electrolyte. The galvanic series of metals and alloys in seawater, which lists common engineering materials in order of their corrosion potential from most active to most noble, has been extensively characterized and is widely used as a guide for avoiding problematic galvanic couples in engineering design. Crevice corrosion is a form of localized corrosion that occurs within confined spaces or crevices where the access of the bulk electrolyte is restricted. Such crevices commonly occur at the interfaces between overlapping metal sheets, under gaskets or seals, beneath deposits of corrosion products or other debris, and at bolted or riveted joints. The mechanism of crevice corrosion involves the depletion of dissolved oxygen within the crevice, which causes the cathodic reaction to shift to the exterior surface of the metal outside the crevice. The interior of the crevice becomes entirely anodic, and the dissolution of metal within the crevice produces metal cations that hydrolyze to form acidic solutions. The resulting drop in pH within the crevice, which can reach values as low as 2 or 3 in severe cases, further accelerates the anodic dissolution and establishes a self-sustaining cycle of accelerating corrosion. The combination of low pH, high metal ion concentration, and high chloride concentration, the latter resulting from the electromigration of chloride ions into the crevice to maintain electrical neutrality, creates an extremely aggressive environment within the crevice that can produce penetration rates many times greater than those observed on freely exposed surfaces. Pitting corrosion is perhaps the most insidious form of localized corrosion, because it produces deep, narrow cavities in the metal surface that can penetrate the full thickness of a component while leaving the surrounding surface apparently intact. Pitting typically initiates at weak points in the passive oxide film on the metal surface, and once a pit has formed, the local chemistry within the pit evolves in much the same way as described above for crevice corrosion, with the accumulation of acidic, chloride-rich solution within the pit driving its continued growth. The growth rate of pits is highly variable and depends on numerous factors, but penetration rates of several millimeters per year have been reported for carbon steel in aggressive environments. The statistical nature of pitting corrosion, with pits varying widely in depth even on a single specimen, makes it particularly challenging to predict the maximum penetration depth from short-term exposure tests, and this has led to the development of extreme value statistical methods for the analysis of pitting data. Stress corrosion cracking is a particularly dangerous form of corrosion failure that occurs when a susceptible material is simultaneously subjected to a tensile stress and exposed to a specific corrosive environment. Under these conditions, cracks can initiate and propagate through the material at stress levels well below the yield strength, and the cracking can proceed at rates that are orders of magnitude faster than would be predicted from either the mechanical loading or the corrosive environment alone. For carbon and low-alloy steels, stress corrosion cracking has been observed in a variety of environments, including hot concentrated hydroxide solutions, which is known as caustic cracking and was historically a significant cause of boiler explosions. Nitrate solutions, which cause a form of stress corrosion cracking that has been observed in carbon steel storage tanks and pipelines, and hydrogen sulfide containing environments, where the cracking mechanism involves the absorption of atomic hydrogen into the metal lattice. The catastrophic nature of stress corrosion cracking failures, which can occur without warning and with catastrophic consequences, has made this phenomenon the subject of intense research and engineering scrutiny, particularly in the nuclear, Petrochemical and aerospace industries. Microbiologically influenced corrosion, which is commonly abbreviated as MIC, is a form of corrosion in which microorganisms, including bacteria, archaea, and fungi, play a direct or indirect role in initiating, facilitating, or accelerating the corrosion process. The most extensively studied microorganisms in the context of MIC are the sulfate-reducing bacteria, which are anaerobic organisms that obtain energy by reducing sulfate ions to sulfide ions. The sulfide ions produced by these bacteria react with iron to form iron sulfide, which is cathodic with respect to iron and thereby establishes a galvanic couple that accelerates the anionic dissolution of the iron. Sulfate-reducing bacteria are ubiquitous in anaerobic environments, such as waterlogged soils, sediments, and the interior of biofilms that form on metal surfaces in aqueous environments, and they have been implicated in the corrosion failure of buried pipelines, offshore structures, water distribution systems, and many other types of infrastructure. Other microorganisms that have been associated with the corrosion of iron include the iron-oxidizing bacteria, which obtain energy by oxidizing ferrous iron to ferric iron and can thereby accelerate the anionic dissolution of metallic iron. The sulfur-oxidizing bacteria, which produce sulfuric acid as a metabolic product and can create highly acidic local environments on metal surfaces, and the acid-producing bacteria, which generate various organic acids as metabolic byproducts. The corrosion rates associated with microbiologically influenced corrosion can be extraordinarily high, with penetration rates of several millimeters per year having been reported in severe cases. And the economic cost of MIC has been estimated to account for approximately 20 to 30% of all corrosion costs in certain industries, particularly those involving water and wastewater infrastructure. The interaction between multiple corrosion accelerating factors can produce corrosion rates that are far greater than would be predicted from the effects of any single factor acting alone. For example, the combination of high humidity, elevated temperature, marine salt deposition, and atmospheric pollution creates an extremely aggressive environment for iron and steel, as is commonly encountered in tropical coastal industrial areas. In such environments, the corrosion rate of unprotected carbon steel can exceed 500 micrometers per year, which corresponds to a mass loss of approximately 3.9 kilograms per square meter per year. At such rates, a structural steel member with an original thickness of 10 millimeters would lose half its cross-section in just 10 years. With potentially catastrophic consequences for the structural integrity of the component and the safety of the people and property that depend on it, given the enormous economic and structural consequences of iron corrosion. It is not surprising that a vast array of methods and technologies have been developed over the centuries for the prevention or mitigation of rust formation, and these methods can be broadly categorized into several principal approaches, including the application of protective coatings, the use of galvanization, cathodic protection, alloying with corrosion-resistant elements, and the use of chemical inhibitors. Each of these approaches operates through a different mechanism, and each has its own advantages, limitations, and range of applicability, and in practice. The most effective corrosion protection strategies often involve the use of two or more of these methods in combination. The most widely used method of protecting iron and steel from corrosion is the application of protective coatings, which are materials that are applied to the surface of the metal to isolate it from the corrosive environment. The most common type of protective coating is paint, which has been used for the protection of iron and steel surfaces for centuries, and which remains the single most important corrosion protection technology in terms of the area of metal surface protected. The global market for protective and marine coatings was estimated at approximately $31.5 billion United States dollars in the year 2023. Reflecting the enormous scale at which paint and related coatings are used for corrosion protection. A modern protective paint system for steel typically consists of 3 layers: a primer, which is applied directly to the prepared metal surface, and which provides adhesion and corrosion inhibition; an intermediate coat or build coat, which provides the required total film thickness and barrier protection; and a top coat or finish coat, which provides resistance to weathering, ultraviolet radiation, and chemical exposure, as well as the desired aesthetic appearance. The total dry film thickness of a complete paint system may range from approximately 100 micrometers for a simple architectural coating to 500 micrometers or more for a heavy-duty industrial or marine coating system. The mechanism by which paint protects steel from corrosion is primarily one of barrier protection, meaning that the paint film physically separates the metal surface from the corrosive environment, preventing the access of water, oxygen, and aggressive ions to the metal surface. However, no paint film is perfectly impermeable, and all organic coatings allow some degree of permeation of water and oxygen over time. The rate of permeation depends on the type of polymer matrix used in the paint, the pigment volume concentration, the quality of application, and the presence or absence of defects such as pinholes, holidays, or areas of insufficient film thickness. In addition to barrier protection, many primers contain active corrosion-inhibiting pigments that provide an additional level of protection by releasing inhibitive species that interfere with the corrosion reactions. Traditionally, the most effective corrosion-inhibiting pigment was red lead, which is a mixture of lead tetroxide and lead monoxide, but the use of lead-based pigments has been largely discontinued due to their toxicity. Modern corrosion-inhibiting pigments include zinc phosphate, zinc chromate, calcium zinc molybdate, and various proprietary formulations. Powder coating is another important method of applying protective coatings to steel surfaces. In this process, a finely ground powder of thermoplastic or thermosetting polymer is applied to the metal surface using an electrostatic spray gun, which imparts an electrical charge to the powder particles, causing them to adhere to the grounded metal surface. The coated part is then heated in an oven to a temperature typically in the range of 160 to 210 degrees Celsius, at which the powder particles melt, flow together, and cure to form a continuous, uniform coating. Powder coating offers several advantages over liquid paint, including the elimination of volatile organic compound emissions during application, the ability to achieve relatively thick coatings in a single application, and a high degree of uniformity and consistency in the finished coating. The typical film thickness achieved by powder coating ranges from approximately 50 to 150 micrometers. Enameling, also known as vitreous enameling or porcelain enameling, is a process in which a glass-like coating is fused to the surface of steel at high temperatures, typically in the range of 750 to 900 degrees Celsius. The resulting coating is extremely hard, chemically resistant, and impervious to moisture, providing excellent corrosion protection in aggressive environments. Enameled steel is widely used for applications such as bathtubs, kitchen appliances, storage tanks for chemicals, and architectural panels. The principal disadvantage of enameled coatings is their susceptibility to chipping and cracking upon mechanical impact, which can expose the underlying steel to corrosion. Galvanization is one of the oldest and most effective methods of protecting iron and steel from corrosion, and it involves the application of a coating of metallic zinc to the steel surface. The term galvanization derives from the name of the Italian scientist Luigi Galvani, though the process itself was developed independently by the French chemist Stanislas Sorel, who patented the hot-dip galvanizing process in 1836. The effectiveness of zinc as a protective coating for steel derives from two distinct mechanisms. First, the zinc coating provides barrier protection in the same manner as any other coating, physically separating the steel from the corrosive environment. And second, and more importantly, the zinc provides sacrificial or cathodic protection to the steel, meaning that in the event that the coating is scratched, damaged, or otherwise breached, exposing the underlying steel, the zinc will preferentially corrode in place of the steel, protecting the steel from corrosion at and adjacent to the damaged area. The sacrificial protection provided by zinc is a consequence of the fact that zinc has a more negative electrochemical potential than iron. With a standard electrode potential of negative 0.76 volts versus the standard hydrogen electrode, compared to negative 0.44 volts for iron. When both metals are exposed to an electrolyte at a damaged area in the zinc coating, they form a galvanic couple in which the zinc acts as the anode and corrodes preferentially, while the iron acts as the cathode and is protected from corrosion. This galvanic protection extends for a distance of several millimeters beyond the edge of the damaged area, meaning that small scratches and minor damage to the coating do not result in the corrosion of the underlying steel. The corrosion product of zinc, which is a white or grayish-white substance composed primarily of zinc hydroxide, zinc carbonate, and basic zinc carbonate, is sometimes referred to as white rust, though it is fundamentally different in composition and properties from the iron oxide rust that forms on unprotected steel. The most common method of galvanization is the hot dip process, in which the steel article to be coated is immersed in a bath of molten zinc maintained at a temperature of approximately 450 degrees Celsius. which is slightly above the melting point of zinc at 419.5 degrees Celsius. The steel is typically held in the zinc bath for a period ranging from a few seconds for thin sheet steel to several minutes for heavy structural sections, during which time a metallurgical bond forms between the zinc and the steel through the formation of a series of zinc-iron intermetallic layers at the interface. These intermetallic layers, which include the gamma phase with the approximate composition phase En3, the delta phase with the approximate composition phase En7, and the zeta phase with the approximate composition phase En13, have hardnesses that range from approximately 170 to 505 on the diamond pyramid hardness scale, and they contribute to the abrasion resistance and mechanical durability of the galvanized coating. The outer layer of the coating consists of essentially pure zinc, which has a hardness of approximately 70 on the diamond pyramid hardness scale. The total thickness of a hot-dip galvanized coating is typically in the range of 45 to 150 micrometers, depending on the thickness and composition of the steel substrate and the immersion time. Electrogalvanizing is an alternative galvanization process in which the zinc coating is deposited on the steel surface by electroplating from an aqueous zinc salt solution. In this process, the steel article to be coated is made the cathode in an electrochemical cell, and zinc is deposited on its surface by the reduction of zinc ions from the electrolyte. Electrogalvanizing produces a thinner, more uniform coating than hot-dip galvanizing, with typical coating thicknesses in the range of 5 to 25 micrometers, and the resulting coating has a smoother, brighter appearance that is often preferred for aesthetic reasons. However, the thinner coating provides a shorter service life than hot-dip galvanizing in most atmospheric environments. The expected service life of a galvanized coating is primarily determined by the rate at which the zinc is consumed by corrosion, which depends on the atmospheric environment to which it is exposed. In a clean rural atmosphere, the corrosion rate of zinc is approximately 0.5 to 1.5 micrometers per year, and a hot-dip galvanized coating with a thickness of 85 micrometers, which is a typical value for structural steel, would be expected to provide protection for approximately 60 to 170 years before the zinc is completely consumed. In an industrial or marine atmosphere, the corrosion rate of zinc is considerably higher, typically in the range of 2 to 8 micrometers per year, and the expected coating life is correspondingly shorter, in the range of 10 to 40 years. These are approximate values, and the actual service life of a galvanized coating depends on many factors in addition to the atmospheric corrosion rate, including the frequency and severity of mechanical damage, the presence of crevices or other geometric features that promote localized corrosion, and the specific composition of the zinc coating. Cathodic protection is a corrosion prevention technique that operates by making the entire surface of the metal structure to be protected into the cathode of an electrochemical cell, thereby suppressing the anodic dissolution reaction that is responsible for corrosion. There are two principal methods of cathodic protection: the sacrificial anode method and the impressed current method. The sacrificial anode method, which has already been discussed briefly in the context of galvanization, involves connecting the steel structure to a block of a more active metal, typically zinc, magnesium, or aluminum, which corrodes preferentially and provides a flow of galvanic current that polarizes the steel surface to a potential at which corrosion is suppressed. The sacrificial anodes are consumed in the process and must be periodically replaced, with a replacement interval depending on the size of the anodes, the current demand of the structure, and the resistivity of the electrolyte. The impressed current method of cathodic protection uses an external power supply, typically a transformer rectifier, to force a direct current to flow from an inert or semi-inert anode through the electrolyte to the steel structure to be protected. The anodes used in impressed current systems are typically made of materials such as high silicon cast iron, graphite, platinized titanium, or mixed metal oxide-coated titanium, which dissolve at very low rates under the anodic conditions of operation. The impressed current method is capable of providing much larger protective currents than the sacrificial anode method, making it suitable for the protection of large structures such as pipelines, ship hulls, offshore platforms, and reinforced concrete structures. The Trans-Alaska Pipeline System, which extends for approximately 1,288 kilometers from Prudhoe Bay on the Arctic coast to the Port of Valdez on the southern coast of Alaska, is protected by one of the largest cathodic protection systems in the world, incorporating both sacrificial anodes and impressed current systems along its length. The use of alloying to improve the corrosion resistance of iron is one of the most important strategies in the field of corrosion engineering, and the most significant development in this area has been the invention and refinement of stainless steel. Stainless steel is a family of iron-based alloys that contain a minimum of approximately 10.5% chromium by mass, and it is the presence of chromium in this concentration that gives stainless steel its characteristic resistance to corrosion. The chromium in stainless steel reacts with oxygen in the atmosphere or in aqueous solution to form a very thin, transparent, and extremely adherent film of chromium oxide, Cr2O3, on the surface of the alloy. This passive film, which has a thickness of only approximately 1 to 5 nanometers, is dense, continuous, and self-healing, meaning that if it is mechanically damaged, it reforms almost instantaneously in the presence of oxygen. The passive film provides an extremely effective barrier against the transport of metal ions from the alloy surface into the solution, reducing the corrosion rate by a factor of approximately 1 million compared to the same alloy without the passive film. The discovery of stainless steel is generally attributed to Harry Burley of Sheffield, England, who in 1913 was investigating the development of erosion-resistant alloys for gun barrels and noticed that a sample containing approximately 12.8% chromium and 0.24% carbon did not rust when exposed to the atmosphere. However, similar observations had been made independently by other researchers in Germany and France at approximately the same time, and the development of stainless steel is perhaps better described as a convergent discovery rather than the work of a single inventor. Today, the global production of stainless steel exceeds 58 million metric tons per year, and stainless steels are used in an enormous range of applications. From kitchen utensils and surgical instruments to chemical processing equipment and nuclear power plant components. Weathering steel, which is also known by the trade name COR10, is a class of low-alloy steel that has been designed to form a stable, protective rust layer when exposed to the atmosphere, thereby eliminating the need for painting or other surface protection. Weathering steel contains small additions of elements such as copper, typically 0.25 to 0.55%, chromium, typically 0.30 to 1.25%, nickel, typically up to 0.65%, and phosphorus, typically 0.07 to 0.15%, in addition to the carbon and manganese that are present in ordinary structural steel. These alloying additions modify the composition and structure of the rust layer that forms on the steel surface, producing a dense, adherent patina that is much less porous than the rust that forms on ordinary carbon steel and that provides a significantly more effective barrier against the further ingress of moisture and oxygen. The development of the protective patina on weathering steel requires alternate cycles of wetting and drying, and the full development of the patina typically requires 2 to 5 years of atmospheric exposure, depending on the specific environmental conditions. During this period, the appearance of the steel changes progressively from the bright metallic finish of the newly exposed steel, through various shades of orange and brown, to the characteristic dark chocolate brown color of the mature patina. The corrosion rate of weathering steel in a typical atmospheric environment decreases markedly as the patina develops, eventually reaching a steady-state value that is approximately 1/4 to 1/2 that of ordinary carbon steel. Weathering steel has been widely used for the construction of bridges, buildings, and other exposed structures, with notable examples including the United States Steel Tower in Pittsburgh, Pennsylvania, completed in 1970. And the Angel of the North sculpture by Anthony Gormley in Gateshead, England, erected in 1998. It is important to note that the protective patina on weathering steel does not develop properly in all environments. In marine environments, where the deposition of chloride salts prevents the formation of a stable patina, weathering steel corrodes at rates similar to or even greater than those of ordinary carbon steel, and its use in such environments without additional protection is not recommended. Similarly, in environments where the steel surface remains continuously wet without the drying cycles that are necessary for patina development, or in environments where the steel is in contact with soil or immersed in water, the use of weathering steel without supplementary corrosion protection is generally inadvisable. Vapor corrosion inhibitors, which are also known as volatile corrosion inhibitors and are commonly abbreviated as VCI, represent a somewhat more specialized approach to the prevention of iron and steel corrosion. Vapor corrosion inhibitors are chemical compounds that have a sufficiently high vapor pressure to sublime or evaporate from a solid or liquid carrier and disperse through the atmosphere within an enclosed space, where they adsorb onto the surfaces of the metal to be protected and form a thin, invisible, molecular-scale film that inhibits the corrosion reactions. The inhibitive film formed by VCI compounds is typically only 1 to a few molecules thick, yet it is sufficient to provide effective corrosion protection for periods ranging from months to several years. Depending on the specific VCI compound used, the concentration of the vapor, and the severity of the corrosive environment. Common VCI compounds include various amine salts of carboxylic acids, such as dicyclohexylamine nitrite and cyclohexylamine carbonate, as well as certain heterocyclic nitrogen compounds such as benzotriazole and its derivatives. These compounds are typically incorporated into packaging materials such as paper, plastic film, or foam, from which they gradually release their inhibitive vapors into the enclosed airspace surrounding the metal object to be protected. VCI-impregnated packaging materials are widely used for the protection of metal parts during storage and shipment, and they offer the advantage of providing corrosion protection without the need for the application of greases, oils, or other contact inhibitors that would need to be removed before the parts could be used. The selection of the most appropriate corrosion protection method for a given application depends on a multitude of factors, including the type of metal to be protected, the nature and severity of the corrosive environment, the required service life, the accessibility of the structure for maintenance and repair, the aesthetic requirements, and the economic constraints. In many cases, the most effective and economical approach involves the use of a combination of protection methods. For example, the corrosion protection system for a modern highway bridge might include the use of weathering steel for the structural members, hot-dip galvanization for the fasteners, and miscellaneous hardware. A multi-coat paint system for areas that are shielded from the atmosphere and therefore unable to develop a proper weathering steel patina, cathodic protection for the substructure elements in contact with soil or water, and the use of stainless steel reinforcement or epoxy-coated reinforcement in the concrete deck. Such a multi-layered approach to corrosion protection, sometimes referred to as a defense-in-depth strategy, provides multiple barriers against corrosion and ensures that the failure of any single protection measure does not result in the rapid onset of corrosive deterioration. The effectiveness of any corrosion protection system is ultimately dependent on the quality of the surface preparation that is carried out before the protective measures are applied. For coatings and galvanized layers to perform as intended, the steel surface must be thoroughly cleaned of all mill-scale, existing rust, grease, oil, and other contaminants that could interfere with the adhesion of the protective layer. The most effective method of surface preparation for steel is abrasive blast cleaning, in which a stream of abrasive particles, such as steel grit, steel shot, garnet, or aluminum oxide, is propelled at high velocity against the steel surface using compressed air or centrifugal force. The impact of the abrasive particles removes surface contaminants and produces a clean, roughened surface profile that provides excellent adhesion for subsequently applied coatings. The degree of surface cleanliness achieved by blast cleaning is classified according to various national and international standards, with the most widely used being the ISO 8501 series and the SSB/CSB series. The highest grade of blast cleaning specified in these standards, known as SAW3 in ISO 8501 or SSB/CSB 5 in the American system, requires that the blast clean surface be free of all visible rust, mill scale, paint, and other foreign matter presenting a uniform metallic appearance. The economic impact of corrosion on the global economy is staggering in its magnitude, and numerous studies conducted over the past several decades have attempted to quantify this cost with varying degrees of precision and comprehensiveness. The most frequently cited estimate is that the total cost of corrosion amounts to approximately 3 to 4% of the gross domestic product of industrialized nations, a figure that was first established by studies conducted in the United States and the United Kingdom in the 1970s, and that has been broadly confirmed by subsequent studies in other countries. In the United States, a comprehensive study conducted by NACE International, now known as the Association for Materials Protection and Performance, in cooperation with the Federal Highway Administration and published in 2002, estimated that the total annual cost of corrosion in the United States was approximately $276 billion, which at that time represented approximately 3.1% of the national gross domestic product. Adjusting this figure for inflation and economic growth, the current annual cost of corrosion in the United States is estimated to exceed $500 billion. Globally, the annual cost of corrosion has been estimated at approximately 2.5 trillion United States dollars, making corrosion one of the most costly problems facing the world economy. These enormous costs include the direct costs of corrosion, which encompass the expense of replacing corroded structures and equipment, the cost of corrosion prevention measures such as coatings, cathodic protection, and the use of corrosion-resistant alloys, and the cost of corrosion-related maintenance and inspection activities. They also include the indirect costs of corrosion, which are more difficult to quantify, but which may be even larger than the direct costs, and which include the cost of lost productivity during shutdowns for corrosion-related repairs, the cost of environmental damage resulting from the release of hazardous materials through corroded containment vessels and pipelines, the cost of personal injuries and fatalities resulting from corrosion-related structural failures, and the cost of overdesign, meaning the additional material and weight that is incorporated into structures and equipment to provide a corrosion allowance that accounts for the expected loss of metal thickness over the service life. The infrastructure sector accounts for a particularly large share of the total cost of corrosion, with bridges being among the most costly infrastructure elements in terms of corrosion-related expenditure. In the United States alone, there are approximately 617,000 highway bridges, of which approximately one-third are constructed of steel or have steel components. A significant proportion of these steel bridges suffer from corrosion-related deterioration and the cost of maintaining, repairing, and replacing corrosion-damaged bridges in the United States has been estimated at approximately $13.6 billion per year. The problem is particularly acute for bridges in northern states, where the application of de-icing salts during winter creates an extremely aggressive corrosive environment for the bridge components. The history of engineering is marked by numerous notable failures that can be attributed, in whole or in part, to the effects of corrosion, and these failures serve as sobering reminders of the consequences of inadequate corrosion management. One of the most significant corrosion-related failures in recent history was the collapse of the Silver Bridge over the Ohio River at Point Pleasant, West Virginia, on December 15, 1967. This I-bar chain suspension bridge, which had been in service since 1928, collapsed without warning during the evening rush hour, killing 46 people. The investigation that followed determined that the collapse was initiated by the failure of a single bar in the suspension chain, and that this failure was caused by a combination of stress corrosion cracking and corrosion fatigue in the high-carbon steel of the I-bar. The corroded area that initiated the fracture was located in a region that was inaccessible for inspection, and the crack had grown to a critical size over many years before the final catastrophic failure occurred. The Silver Bridge collapse led directly to the establishment of the National Bridge Inspection Standards in the United States, which mandated regular inspection of all highway bridges at intervals not exceeding 2 years. Pipeline corrosion is another area where the consequences of corrosion failure can be catastrophic, both in terms of economic loss and environmental damage. The transportation of petroleum and natural gas through underground and underwater pipelines is essential to the global energy infrastructure, and the total length of oil and gas pipelines worldwide exceeds 3.5 million kilometers. These pipelines are subject to both external corrosion, caused by the soil or water in which they are buried or submerged, and internal corrosion, caused by the transported fluids, which may contain water, carbon dioxide, hydrogen sulfide, and other corrosive species. Corrosion-related pipeline failures can result in explosions, fires, oil spills, and environmental contamination, and the cost of pipeline corrosion in the United States alone has been estimated at approximately $9 billion per year. One of the most dramatic examples of pipeline corrosion failure was the rupture of a corroded pipeline in the Prudhoe Bay oil field in Alaska on March 2, 2006, which resulted in the spill of approximately 212,000 gallons, or approximately 5,053 barrels, of crude oil onto the tundra of the North Slope. The spill was caused by internal corrosion of the pipeline, which had not been adequately monitored or maintained. The operator of the pipeline, BP Exploration Alaska, was subsequently fined $20 million by the United States government and agreed to pay an additional $12 million in restitution for the environmental damage caused by the spill. The restoration of the Statue of Liberty, which was carried out between 1984 and 1986 in preparation for the statue's centennial celebration, provides a fascinating case study in the corrosion of dissimilar metals. The Statue of Liberty, which was designed by the French sculptor Frédéric Auguste Bartholdi and engineered by Gustave Eiffel, consists of an outer skin of copper sheets approximately 2.4 millimeters thick, which is supported by an internal framework of wrought iron ribs and armature bars. When the statue was originally constructed, the copper skin was insulated from the iron framework by a layer of shellac-impregnated asbestos cloth, which was intended to prevent galvanic corrosion between the two dissimilar metals. Over the course of nearly a century of exposure to the marine atmosphere of New York Harbor, however, this insulating barrier had deteriorated, and extensive galvanic corrosion of the iron framework had occurred. The iron ribs and armature bars had lost approximately two-thirds of their original thickness in the most severely corroded areas, and the structural integrity of the statue was seriously compromised. The restoration project involved the replacement of approximately 1,800 corroded iron armature bars with new bars made of Type 316L stainless steel, which is a molybdenum-bearing austenitic stainless steel with excellent resistance to corrosion in marine environments. The new stainless steel bars were insulated from the copper skin by Teflon tape to prevent galvanic corrosion between the stainless steel and the copper. The total cost of the restoration was approximately $87 million in 1986 dollars, a significant portion of which was attributable to the repair of corrosion damage. The restoration project also revealed an interesting and unexpected finding. The copper skin of the statue, which had been expected to be severely corroded after nearly a century of exposure to the marine atmosphere, was in fact in remarkably good condition, having lost only approximately 0.127 millimeters of its original 2.4 millimeter thickness. This is because copper, like zinc, forms a protective patina of corrosion products, in this case a green layer of copper carbonate and copper chloride compounds known as verdigris, that significantly reduces the rate of further corrosion. The testing and evaluation of the corrosion resistance of metals and protective coatings is an essential activity in the field of corrosion engineering, and a wide variety of standardized test methods have been developed for this purpose. One of the most widely used accelerated corrosion tests is the salt spray test, which is also known as the salt fog test and which is described in the international standard ISO 9227 and the American standard ASTM B117. In this test, specimens of the material or coating to be evaluated are placed in a closed chamber and continuously exposed to a fine mist of a 5% sodium chloride solution at a temperature of 35 degrees Celsius. The duration of the test varies depending on the material and the specification being evaluated, but typical test durations range from 24 hours to several thousand hours. The specimens are periodically examined for evidence of corrosion, blistering, or other forms of deterioration, and the time to the first appearance of rust or other corrosion products is recorded. While the salt spray test is widely used and is specified in numerous industrial and military specifications, it has significant limitations as a predictor of real-world corrosion performance. The constant exposure to salt fog at elevated temperature that characterizes the salt spray test is quite different from the cyclic wetting and drying temperature fluctuations, and varying pollutant concentrations that characterize natural atmospheric exposure, and the correlation between salt spray test results and actual field performance is often poor. This has led to the development of more sophisticated accelerated corrosion tests that attempt to more closely simulate natural atmospheric conditions, such as the Prohesion test and various cyclic corrosion tests that incorporate alternating periods of salt fog exposure, drying, and humidity exposure. Electrochemical impedance spectroscopy, commonly abbreviated as EIS, is a more fundamental and informative technique for the evaluation of corrosion behavior. In this method, a small sinusoidal voltage perturbation, typically with an amplitude of 5 to 10 millivolts, is applied to the specimen at a range of frequencies, typically from 100 kHz to 10 mHz, and the resulting current response is measured. The ratio of the voltage perturbation to the current response at each frequency defines the impedance of the electrochemical system, which is a complex quantity having both a real and an imaginary component. The impedance data are typically plotted in the form of a Nyquist plot, which displays the imaginary component of the impedance on the vertical axis versus the real component on the horizontal axis, or a Bode plot, which displays the magnitude and phase angle of the impedance as functions of frequency. The shape and magnitude of these plots provide detailed information about the corrosion rate, the properties of the corrosion product layer, and the integrity of any protective coating on the metal surface. The phenomenon of corrosion has also found a place in the world of art and aesthetics, where the unique visual qualities of rust and patina have been deliberately employed by artists and architects to create works of distinctive character and beauty. The use of weathering steel in architecture and sculpture has already been mentioned, and artists such as Richard Serra, whose monumental weathering steel sculptures are displayed in public spaces and museums around the world, have exploited the rich, warm colors and textured surfaces of oxidized steel as an essential element of their artistic expression. Serra's massive weathering steel sculptures, some of which weigh hundreds of tons and stand many meters tall, are designed to develop a deep, dark rust patina over time, and the gradual change in the appearance of the sculpture as the patina evolves is considered an integral part of the artistic experience. In the field of archaeology, the study of corrosion and rust is of fundamental importance for the preservation and interpretation of ferrous artifacts recovered from archaeological sites. Iron artifacts that have been buried in soil or submerged in water for centuries or millennia are typically found in a heavily corroded state, and the rust that encases them often preserves important information about the original shape, surface decoration, and manufacturing techniques of the object. The careful study and conservation of corroded iron artifacts requires a detailed understanding of the corrosion processes that have occurred over the long burial period, including the identification of the specific corrosion products present, the determination of the extent of metal loss, and the assessment of the stability of the remaining metal and corrosion products. Techniques such as X-ray radiography, X-ray diffraction, Raman spectroscopy, and metallographic examination are routinely used in the conservation laboratory to characterize the condition of corroded iron artifacts and to guide the selection of appropriate conservation treatments. One of the most remarkable examples of iron preservation in the archaeological record is the Iron Pillar of Delhi, which stands in the Kut complex in Mehrauli, Delhi, India. This pillar, which is approximately 7.21 meters tall and weighs approximately 6.5 metric tons, was erected in approximately 400 CE during the reign of the Gupta Emperor Chandragupta II. Despite having been exposed to the open atmosphere for more than 1,600 years, the iron pillar exhibits remarkably little corrosion, a fact that has been the subject of considerable scientific investigation and popular wonder. Studies of the pillar have revealed that its corrosion resistance is attributable to the formation of a protective passive film of iron hydrogen phosphate hydrate, also known as mesowite, on the surface of the pillar. The formation of this protective film has been attributed to the high phosphorus content of the iron, approximately 0.25%, which is higher than that of modern steels, and which is a consequence of the ancient Indian iron smelting process that used phosphorus-rich iron ores and charcoal fuel. The phosphorus in the iron promotes the formation of the stable iron phosphate film, which provides a much more effective barrier against corrosion than the porous rust that forms on ordinary carbon steel. The study of corrosion extends beyond the confines of Earth, and the investigation of corrosion processes on other planets, particularly Mars, has been a subject of increasing scientific interest in the context of planetary exploration and the potential future human colonization of Mars. The surface of Mars, as observed by orbital spacecraft and surface rovers, is characterized by a reddish color that is attributable to the presence of fine-grained iron oxide minerals, primarily nanophase hematite and various iron oxyhydroxide phases, in the Martian soil and dust. The formation of these iron oxides is a consequence of the oxidation of iron-bearing minerals in the Martian surface materials, a process that has been occurring over billions of years. The Martian environment presents a unique set of conditions for corrosion that differ significantly from those encountered on Earth. The Martian atmosphere is composed primarily of carbon dioxide, approximately 95.3%, with minor amounts of nitrogen, approximately 2.7%, and argon, approximately 1.6%. The atmospheric pressure on Mars is only approximately 610 pascals, which is less than 1% of the atmospheric pressure on Earth. The temperature on Mars varies widely, from a minimum of approximately -153 degrees Celsius at the winter polar caps to a maximum of approximately 20 degrees Celsius at the equator during summer, with a mean surface temperature of approximately -60 degrees Celsius. Liquid water is not stable on the Martian surface under present conditions, although there is evidence that liquid water existed on Mars in the distant past and that small quantities of liquid brines may form transiently under certain conditions. The corrosion of iron and steel materials used in spacecraft and surface equipment on Mars is therefore expected to be very different from that observed on Earth. In the absence of liquid water, the conventional electrochemical corrosion mechanism described in earlier sections of this narrative cannot operate, and the corrosion rate of iron in the current Martian environment is expected to be extremely low. However, the Martian atmosphere does contain trace amounts of water vapor and hydrogen peroxide, and the Martian soil contains various oxidizing species, including perchlorate salts, that could potentially contribute to the degradation of metallic materials over extended periods. The study of the corrosion behavior of structural materials in simulated Martian environments is an active area of research, with implications for the long-term integrity of spacecraft, habitats, and other infrastructure that may one day be deployed on the Martian surface. The phenomenon of corrosion in space environments beyond Mars is also of interest, particularly in the context of the long-duration missions that will be required for the exploration of the outer solar system. In the vacuum of deep space, the primary mechanisms of material degradation are not electrochemical corrosion, but rather atomic oxygen erosion, which is significant in low Earth orbit. Radiation damage from cosmic rays and solar particle events, and micrometeorite impacts. However, within the pressurized habitable volumes of spacecraft, where an atmosphere similar to that of Earth is maintained, conventional corrosion can occur, and the management of humidity and the prevention of condensation on metallic surfaces are important considerations in spacecraft environmental control system design. Returning to terrestrial concerns, the corrosion of iron and steel in reinforced concrete structures deserves special mention, as it is one of the most economically significant forms of corrosion in the modern world. Reinforced concrete is the most widely used construction material in the world, and the corrosion of the steel reinforcement within the concrete is the single most common cause of the premature deterioration of reinforced concrete structures. As previously noted, the highly alkaline environment of the concrete pore solution, with a pH typically in the range of 12.5 to 13.5, normally maintains the steel reinforcement in a passive state in which the corrosion rate is negligibly low. However, this passive state can be destroyed by two principal mechanisms: the ingress of chloride ions from de-icing salts or seawater, which can penetrate through the concrete cover and accumulate at the surface of the reinforcing steel in sufficient concentration to break down the passive film, and the carbonation of the concrete, which is a slow chemical reaction between the carbon dioxide in the atmosphere and the calcium hydroxide in the concrete pore solution that gradually reduces the pH of the concrete to values below approximately 9, at which the passive film on the steel is no longer stable. Once the passive film on the reinforcing steel has been destroyed by either chloride ingress or carbonation, active corrosion commences, and the rust that forms on the steel surface occupies a volume approximately 2 to 6 times greater than the volume of the steel from which it was formed. This volume expansion generates tensile stresses in the concrete surrounding the reinforcing bar, and because concrete has a relatively low tensile strength, typically in the range of 2 to 5 megapascals, these stresses can cause the concrete to crack, delaminate, and spall, exposing the corroded reinforcement and accelerating the deterioration process. The repair and rehabilitation of corrosion-damaged reinforced concrete structures is extremely expensive, and the global annual cost of this activity has been estimated at several $100 billion. As this long and detailed examination of the science of rust draws toward its conclusion, it is perhaps fitting to observe that the process of corrosion, for all the damage and expense that it causes, is ultimately nothing more than the expression of a fundamental thermodynamic truth. The metallic iron that we extract from its ores and fashion into the structures and machines of our civilization exists in a state of thermodynamic disequilibrium with its environment, and the process of rusting is simply the means by which this disequilibrium is gradually resolved. Every atom of iron that corrodes is merely returning to the stable oxide state from which it was extracted at great expenditure of energy, and in this sense, corrosion is not a defect or a failure, but rather the natural and inevitable consequence of our use of a thermodynamically unstable material in an oxidizing environment. The study of corrosion and the development of methods to prevent or retard it is therefore, at its most fundamental level, a struggle against thermodynamics. A struggle that can never be won outright, but that can be managed through the intelligent application of scientific knowledge and engineering principles. The paints and coatings that we apply to our steel structures, the zinc that we use to galvanize our fasteners and sheet metal, the chromium that we alloy into our stainless steels, and the cathodic protection systems that we install on our pipelines and offshore platforms are all strategies for slowing the inexorable return of iron to its oxide state, for extending the useful life of our iron and steel artifacts in a world that is constantly working to reclaim them. And so the process continues, as it has continued for as long as iron has been worked by human hands, the slow, quiet, patient dissolution of metal into oxide, the gradual transformation of the products of human industry back into the minerals from which they came. In the grand sweep of geological time, the bridges and buildings and ships and machines that we construct from iron and steel are no more than temporary arrangements of atoms, brief interruptions in the eternal cycle of oxidation and reduction that governs the chemistry of iron on the surface of our planet. The rust that forms on a forgotten nail, the rust that slowly consumes an abandoned railway track, the rust that gradually returns a sunken ship to the ocean floor, is simply the universe reasserting its preference for equilibrium, for the lowest energy state, for the quiet stability of iron oxide over the restless reactivity of metallic iron. This has been an examination of the science of rust, and it is hoped that the information presented herein, delivered in the measured and unhurried cadence that is characteristic of this channel, has served its intended purpose, which is to say, to provide a gentle accompaniment to the transition from wakefulness to sleep. The electrochemical reactions that govern the formation of rust will continue to proceed in the darkness, as they always have, slowly and steadily converting the iron of the world back into the oxide from which it came, and there is, perhaps, something comforting in the knowledge that this quiet, relentless process will continue long after the listener has drifted off into peaceful slumber.